Okay, let's continue the opcode stuff. Let me go ahead and delete these now that we got these extra instructions here, and let's move on and take a look at the move W0 lat B instruction. Okay, now move W0 lat B, again you have to look at what kind of instruction it is, and also what does lat b translate to. So lat b is again one instruction in those well, let me go to the data sheet. um, so let me go to page 33, and lat b is somewhere here, right? Lat b is somewhere in the SFR space before the 800, and it's in one of these groups. It's in one of these groups. You can guess that it must be in the IO group, and its address has to be 200 something, right? So let's go ahead and search for latb. And latb's address is 2cc. Okay, so that's the first thing that you want to know. 2cc is the address of latb. And so somewhere you expect a 2cc to appear in the opcode. Now if you want to write down the opcode is 88160. Okay. Now and lat b was 2cc. Okay. And you can see 2cc and 166 is 2cc divided by 2, right? So you can guess what's going on here, right? But we'll get to it in a moment. So now the next question, so the first question that we wanted to ask was, what does latb translate to? What address is it? And we got the 2cc. Now the other question is, what is this move W0 latb instruction? Which one of the categories of the move instruction would it be? So again, Programmer's Reference Manual, page 40. We said move W0 into latb, right? Seems to be this one. Move a wreg, no, sorry, move WNS. It could have been that one too, because W0 is the same as wreg, but let's assume that we are saying move W3 into latb. Then this would be the instruction. So move WNSF, go to page 282. Now the opcode is 8 in hex, which is what we got. And there is a 1 here. So this 1 bit talks about the direction. And if you remember the previous instruction, we had an 8 and a 0 here, because in that case we were moving something from a register to wreg, and we used the 0 there. But here you're saying that the direction is from one of the wregs to that register. So you see a 1 here, right? Now if I put the 2cc here, then I'm going to see 8, 2cc, and then the destination is 0, alright, W0. But again, you can see that it's not 2cc, it's 166, which is again that 2cc divided by 2, and it allows you to specify, let me count the number of bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 bits, plus a hidden 0 that allows you to access a data memory space of 16 bits. And again, let me remind you that we do not have 16 bits of physical memory space. We only have 13 bits of address for the data memory space. The rest of it is used for the shadow reading from the program memory that we will get to in discussion 3. Okay, so we did this instruction. Let's move on, and we can go to the tough instruction now. So the first instruction, bit clear, clock div, #8. Now this one, well, first question, where is clock div? And if you look at the manual, page 44, you're going to see that the address is 744. Okay, so the address for ClockDiff is 744. If you want to write it down somewhere, feel free to do it. And then the other question would be, what is your uh, let's look at the opcode BCLR. And if you look at the programmer's reference manual, I think it would be page 43 that talks about, no, page 45 that talks about bit instructions. And in the bit instructions, you have two bit clears. One is going to be bit clear one of the W registers, and there is another one which says any general purpose registers. By the way, it might be a good idea to go back and forth between these two and see the difference between when you're talking about the general purpose register with addresses from 0 to 1 FFFF or even 16-bit, as opposed to these 4-bit addresses. So if you look at the general purpose register, this is the opcode. You have 1010, 1001, and then bits and a bunch of Fs. And if you look at the bit clear with the W's, then you have 1010, 0001, and then the 4 bits, and then you have the 0, capital B, 000, PPP, SSS. So you see that instead of filling this with Fs, with the addresses, it has a bunch of options here that allow you much more flexibility in working with these registers. And these would be things like indirect addressing and post increment and decrement that is covered later. But essentially that's the difference between your W0 through W15. Those give you a whole lot more flexibility in using them in different modes, as opposed to your regular registers that you have to fill this space with the register address. Okay, so this is the bit clear opcode. So the bit clear opcode is 1010, which is A in hex, and then 1001, which is 9 in hex, followed by 3 B's, the bit number that you want to clear, and the 4th bit here. Very weird, but and of course, I mean, there is no logic in determining the format of opcodes. But the reasons that I don't want to get into, it makes it a little bit easier to read the opcode and translate it, but don't get there. Don't even think about why they chose this format of breaking apart the B's here and this B here. And by the way, one point, if the bit number, and of course, I mean, one thing that makes it more complicated is the .b option here, which says work on this register as a byte and not as a word register. So that brings in a lot of complications. And if you read the descriptions here, it's going to say that if you're doing the byte operation, these 3 would be the only bits that you need, right? Because in a byte, you have at most 8 bits. So you have to be able to encode 0 up to 7, and you can do that with 3 bits. And then this becomes the least significant bit of the address in data memory, because when you're doing byte addressing, your addresses could be odd or even. Now, if you're doing even addresses, then these 3 would be your least significant bits. This would be the most significant bit of the bit number that you want to clear. And then in terms of the address, these would be the address shifted ones. So you basically do not encode the least significant bit, because you know that's going to be 0 in the case of a word operation. Okay, now here's when it gets really complicated and confusing. If you remember with the move stack W15, I said that the address 808 becomes 404 before you put it in there. Here you don't need to shift it, because you already have this B here, and assuming that the bit number that you want to access is less than 8, so this bit is going to be 0 anyway, then if you have an address 808 to work with, just put 808 here and you will be fine. Okay, so let me show you what the PIC microcontroller put in here for bit clear. It says A90745. Okay, and remember, this is bit clear number 8, right? So the bit that you want to clear is going to be 1000. The 1 is going to appear here. 000 is going to appear here. And then you have your 744. So this would be 0, 7, 4, 4, except that B makes it 5. Alright, so that's why you get A90745 as the translation of that. Let me do one thing, and let me just show you this piece of writing that I have, and let me maybe even increase the font here so that you can do a screenshot of this and take a look at it later. So here I'm saying the clock div is 744, so your FFFFFF is going to be 744. Now break it up into these bits. You have a 0 here, and then you have 744, but I haven't highlighted the least significant bit. I put it as green. Now what is the bit number that you want to clear? It's 1000 in binary, and I've shown these in blue and yellow. And when you put this together, you're going to have, these are for the opcode A9, and then you have 0. These are the zeros that you have for your bit. This 1 here of the bit number is here. This is in pink. You have here part of the 744, and this is the 744 plus this one, which is 5. Now, if you're very confused, don't worry, and I'm not going to test you on bit clear and you know, how to come up with the exact opcode, but I just wanted to make you go through this torturous exercise just to get a better understanding of why you need a compiler and why we are so happy to have the compiler do this for us. Okay, now let me do just one more piece of torture, and then I'll stop. Now the next segment is going to talk about branches and how you calculate the address, the jump address for loops and stuff like that. But let me just show you something interesting. So bit set CNPU1 pound 2. Okay, now this is very similar to that bit clear thing that we had up here. Right, so this is very similar to the bit clear, that clock div thing. But let's take a look at what the compiler does. So bit set CNPU1, and CNPU1 is 0068 if you look at the data sheet. And you can see the 68068 here. So let me read it for you. So it's A84068, the bit set. And if I go to the bit set in the program's reference manual, let me go to 45? Yeah. So if I go to bit set, I'm doing this, right? So go to page 152. Now the code is A8 and then the bits, followed by these F's, and then the most significant bit here. Okay, now right now that our bit is number 2, basically that means that this is 0 and these guys are going to be 0, 1, 0. Right, that's the binary number for 2. So let's see what we get here. So in the bit set, we have A8, which is the opcode, A8, and then here we have 4, which does make sense because which is 4 because we had 0, 1, 0, which was bit number 2 that you wanted to set, and F, the address F is 0, so you would get a 4 here because you have 2 followed by 0, so it becomes 4, and so far it does make sense. So we have A8, 4, and then 0, 6, 8, 0, 6, 8 makes sense because we have 6, 8, which is the address of CNPU. Now, you may want to pause the video and think, what happens if I change this, keep everything the same, instead of setting 2, if I say bit number 10, right? So 2 in binary is 0, 0, 1, 0, right? 10 in binary is 1, 0, 1, 0, right? So the only thing that I'm doing here is changing this bit from 0 to 1. You may want to pause the video and tell me what is the right encoding that you expect to see here, and then continue to hear what I'll show you. So pause now. Okay, so as you change this to 10, now the only thing that I expect to change here would be for this to go from A8 4068 to go to 69, because that's the only thing that I'm changing. And here you should see bit set CNPU1, comma, number 10. Now let me compile it, and you're going to see that MPLABX is buggy, and it shows you a different thing as the code in the program memory. Although the opcode is correct, if you run it, the opcode is correct, and the PIC microcontroller is going to do what you expect it to do, which is setting the bit number 10 in CNPU1. It's just that people who wrote the part of the MPLAB IDE that shows you the program memory, they were not careful enough, so the values that you got were wrong. So you can see here, let me see, where is it? After the bit set trace A, you can see that it's saying bit set 0x69 number 2, right? So it basically shows that whoever wrote the part of code that was supposed to go from here to here forgot about this minute detail in the encoding here and assumed that this 1 here appears as part of your F, so that's why they went from 68 to 69, and they're still showing this as bit number 2. Okay, so it's dangerous to rely on MPLABX, but you know, this is what it is, and there's a bug in the implementation of MPLABX. Alright, let me stop here. Now the next and last video that I'm going to record is going to deal with, oh, and by the way, I'm going to skip these, so I assume that you can read the manual and figure out, how to do this. But what I want to tell you is how this branch a loop is encoded, and how does the microcontroller know where to go. Alright, so watch the next video for that.